everyone. My name is Papia and I am the PMRF NPTEL teaching assistant for the course Classical Mechanics of a Single Particle. So the course instructor is Professor Shutotik Banerjee, and today we will talk about week 9 assignment 9 previous year questions with details. Okay, so coming to the first question. So first question tells that generalized coordinates is what, and there are four options of that, like generalized coordinates are always independent of each other, have always have the unit of length, are consistent with holonomic constraints, may or may not be orthogonal, or have a fixed unit. So these four options are there. Now we have to calculate which one is correct for generalized coordinates. Okay, so what are the options are given? First of all, the option is are always independent of each other. That is correct, because let's say generalized coordinates is qy, which is like q1, q2, q3 and dot dot dot. So these q's should be independent to each other. Okay, so the generalized coordinates are always independent of each other. So the first option is correct. Now always have the unit of length. No, it should not be. I mean, it is not necessarily have the same unit for all the generalized coordinates. Okay, so it is not necessarily true that all the generalized coordinates have the same unit, or it is having the same unit of length. So this is not correct. Are consistent with holonomic constant? Yes, that is correct. May or may not be orthogonal or have a fixed unit? Yes, that is also correct. So I just want to mention here coordinates. So what is the thing, like it is should be independent may or may not have the same unit, then are consistent with holonomic constraints. Okay, so this is the case. So let me go for the first question again. So for the first question, we can see that it will be always have independent of each other, correct. Always have a unit of length, it is not correct. Are consistent with holonomic constraints, correct. May or not may not be the orthogonal or have the fixed unit. Okay, so may or may not be the orthogonal, that is also one condition. Okay, I need to write here. May or may not be orthogonal to each other, because you can see that I can have a example for that. So maybe orthogonal, for that case obviously I can have x, y, z, and this condition is x perpendicular y perpendicular z, but may not be orthogonal For this case, I can have the example of curvilinear coordinate. for this case, coordinates are not, sorry, coordinates are not necessarily orthogonal. Okay, so that means I can have the option for 1 is 3 and 4. So that means for question number 1, I will have correct option as correct 1, 3, 4. Okay. Okay. Now coming to the second question. Generalized coordinates are always independent of each other, may or may not have the unit of distance, must always be orthogonal, are always equal in number to the Cartesian coordinates, are always consistent with holonomic constants. So we have already mentioned that the generalized coordinates are always independent of each other. Generalized coordinates are always independent of each other. That is correct. May or may not have the unit of distance. That is also correct. Must always be orthogonal. No, this is not correct. Are always equal in number to the Cartesian coordinates. That is not correct. Are always consistent with holonomic constants. That is correct. So consistent with holonomic constants. Okay, and independent to each other. Independent. And the fifth one is okay, and also okay. So from this case I can see that the option number 1 is correct, 2 is correct, and 5 is correct. Okay, fine. Okay, now we can go for the next question. The number of holonomic constants is equal to the number of generalized coordinates, equal to the mass of the particle, equal to the difference between space dimension and generalized coordinates, always equal to the number of non-holonomic constants. Okay, so what are the holonomic constants we are here talking about? This is, let's say, if like u1, u2, t equals to 0. This is the function, like holonomic constant equation. Function, you can see. So the function is like there will be some u1, u2, these are the generalized coordinates. So now let us go for the options. Equal to the number of generalized coordinates. No, this is not correct. Equal to the mass of the particle, that is also not correct. Equal to the difference between space dimension and generalized coordinates, that is correct. Always equal to the number of non-holonomic constants, that is also not correct. So how we can say, because, so let's say for a n-dimensional particle, let's say, so 3n or something, like if it is an unconstrained DOF or degrees of freedom, and let's say I am talking about generalized coordinates are, let's say, k in number. So then number of holonomic constraints is equals to 3n minus k. So that means unconstrained DOF minus generalized coordinates, that is the number of holonomic constants. So here you can see that equal to the difference between space dimension and generalized coordinates. So I called that unconstrained DOF, that is exactly proportional to the space dimension without imposing any type of constraints on that case. So this, and then so holonomic is equals to space dimension minus generalized coordinates. So the third option is correct. Okay, so now we can go for the next question. A particle of mass m moves under a potential V equals to k by 2 x square plus y square, where k is a constant. How many cyclic coordinates are present? Okay. So first of all, we need to check what is cyclic coordinate. The coordinates which are not present explicitly in Lagrangian, but their time derivative is present in L. These coordinates are cyclic coordinates. Okay, let's say I am talking about L, which is a function of r dot theta dot phi dot r. That's it. So here theta and phi, these are cyclic coordinates. Okay, now coming to the question, V equals to k by 2 x square plus y square. Okay. So always, if it is in 2 dimension, then I can write it like in terms of k by 2 r square, because x square plus y square equals to r square in this case. So our t is half m r dot square plus r square theta dot square. So now you can see that r and theta, these two were there, and I am having my L as t minus v, which is half m r dot square plus r square theta dot square, right, minus k by 2 r square. So from this expression, I am writing here again, this will be minus. So from there we can see that cyclic coordinate is theta, because theta is absent in L but theta dot is present in L. So I can say that theta is cyclic coordinator here. So for this case, how many cyclic coordinates are present? It is 1. Okay? Okay, fine. A pendulum of length L describes a conical motion in 3D space, forming a circle on the horizontal plane. How many generalized coordinates are needed? Okay. So there are options 1, 2, 3, and the fourth one is it depends on the applied force. No, obviously it is not depending on the applied force, because we are not talking about applied force anymore here. Only what we are just talking that pendulum is length L and it describes a conical motion in 3D space and forming a circle on the horizontal plane. These informations are given. So what does this mean? Basically, yes, so I am just drawing a pendulum. Okay, so here conical motion, it is mentioned in question. That means theta is fixed and it is steady rotation. So what does this mean? This means that our theta is constant. How we can say that theta is constant? Because there is one constant is given, that it is moving us in a circle in the horizontal plane. So that means if this is like that and this is like that, so this is the theta, and this will be always constant because we are moving in a circle on the horizontal plane. So theta is constant here, and obviously we know that L is also constant, fixed, because it is a rigid body. So obviously for a pendulum, r theta phi, where what is phi? Phi can vary with time. So here as L is fixed, so r fixed, theta fixed, as it constrained to move in a circle on horizontal plane. And what about phi? Phi can vary as it is a function of t. So what is the, how many generalized coordinates are there? Generalized coordinates is 1, which is 5. So this one is the correct option. How many generalized coordinates are needed? So only the phi is needed, as phi is a function of t and all other r and theta all are constant. Okay, fine. Okay, so now we will go for the question number 6. Okay, so now moving to the 6th question. In the 6th question, what is the question? the particle has kinetic energy T equals to half m after square plus r square theta square. What is the generalized momentum corresponding to theta? Okay. So particle has T as 1 by 2 m vector square plus r square theta square. So what is the generalized momentum corresponding to theta? So what is the expression for generalized? Momentum corresponding to Qi. For this, what is the recipe, which is del n del Qi dot. And if we are talking about only kinetic energy, so it will be del T del Qi dot. Okay. So for this case, what is the T? T is half m r square plus r square theta square. They are asking. So what are the generalized coordinates here? R theta. So generalized momentum corresponding to theta is del T del theta dot, or it can be written as like this one, or d theta. So what will be the expression for d theta? It will be del theta dot of half m vector square plus square theta dot square. So this will be simply half m r square to theta dot. So it is m r square theta dot. So corresponding momentum of generalized coordinate theta is e theta m r square theta dot. Okay, so the answer will be m r square theta dot. That means the option number 2. Okay, so for this case, what we have done, we just what is the question, like particle has kinetic energy T, what is the generalized momentum corresponding to theta? So T we are writing here 1 by 2 vector square plus r square theta square. So generalized momentum corresponding to Qy. In general, it is Py, which is del Qy dot, and which is del T del Qy dot for this condition, because here there is no V, so only the T will be there, because we know that L equals to T minus V, right? So now T equals to half m r square plus r square theta square. So the generalized coordinates is r and theta here, but in the question they are asking the generalized momentum corresponding to theta, corresponding to the generalized coordinate theta. So it is del T del theta dot equals to del theta dot, which is p theta. So p theta will be del theta of half m r square plus r square theta square, which is exactly equal to m r square theta dot. So the corresponding momentum of generalized coordinate theta is p theta equals to m r square theta dot. Okay. Now coming to the next question. A particle moves freely inside a hollow hemisphere without touching its surface. How many degrees the average coordinates are? Okay. So first of all, we need to see the language here. Moves freely inside a hollow hemisphere without touching its surface. So particle moves freely. That means free particle. Then hollow hemisphere. and another one is does not touch the surface or surface. Of hemisphere. Okay, these three were there, right? So, as this is so the generalized coordinate will be 3. So now let's say this is the sphere, hemisphere, hollow hemisphere. So what does this mean? This means that inside of this region, this is hollow. So any particle can move inside of that. So let's say I'm talking about this particle, or maybe I can do a different color here. This one. So this is a particle, so it can move here, anywhere it can move inside that hemisphere. So that means we can have X, Y, Z, these three as a generalized coordinate. Or I can simply write here R, theta, phi. These three also the generalized coordinate. Now one can ask that, okay, let me change the color. This one. Okay. Now one can ask that if let's say this is touching the surface, that means only touching the surface. So only touching the surface means there is a constraint. So if the particle only moves on the surface of hollow hemisphere, then the generalized coordinate will be 2, because there will be one extra constraint imposed on the free particle. Okay, but as this question tells free particle, then what they are asking, what they are telling, hollow hemisphere, and another thing they are telling is does not touch the surface. So these things basically tells me that the generalized coordinate is 3. So this one will be the correct option. A particle moves freely inside a hollow hemisphere without touching its surface. However, the generalized coordinates are required 3. R theta phi. Actually, basically here R theta phi will be the appropriate one, because hemisphere is there, so it will be very much simple for calculating and R theta in terms of R theta phi. So R theta phi will be the generalized coordinate. Now question number 8. For the Lagrangian A equals to t minus b, which of the following assumptions is not used in deriving the Euler-Lagrange equation? Okay, so and the options are generalized coordinates are independent, the mass of the particle is constant, the coordinate system is orthogonal, the particle moves under a scalar potential, the potential may depend on coordinates and time. So basically, if you see, oh sorry, if you see Sir's lecture on derivation of EL equation, so there Sir was mentioning some of the assumptions. The first assumption was there that F will be minus grad phi or plus grad phi. So it is like the scalar potential should be there, but obviously the V can be R and T, there is no problem. On general form of potential V. Okay, very good. So so that means you can see that the particle moves under a scalar potential, that is correct. That means it is the assumption, and it should be there. Now the fifth one is the potential may depend on coordinates and time. Yes, that is fine, because as I told that V can be very general. So V is R T. So this is also true. Should be there. The coordinate system is orthogonal. No, we don't want. It is not useful, because obviously generalized coordinates are not orthogonal. Okay, so this is not used in deriving the equation. Now the mass of the particle is constant, that is also true. Generalized coordinates are independent, that is also true. So I can just summarize here. For deriving EL equation, we need generalized coordinates are independent to each other. Then potential is a function of space and time. Mass of the particle is constant. Now the fourth one is the potential is a scalar potential. Okay, so these are the things. So which one should not use in EL equation? The thing is that the coordinates are orthogonal, because obviously in general form they are not orthogonal, so we don't want need this information. So the answer of this question is 3, because they are saying that it is not used. Okay, so that is this. Okay, now come to the next question. Question number 9. Which of the following assumption is not necessary for deriving the Euler-Lagrangian equation. Okay. So this is exactly similar as the previous one what we were talking. The general coordinates are independent. Yeah. That is true. Needed. The force must be a related of the scalar pressure. That is also true because I told that if force to grad phi should be grad phi should be there. The coordination must be orthogonal. No, not needed. The pressure can depend on generalized velocities. That is also fine in general form. So which is not needed. Is that generalized coordinates are orthogonal to each other. So that is the one which is not necessary. Okay. So now we can see that the coordinate system must be orthogonal. That is not needed. Okay. Okay. So now we move to the question number 10. So what is question number 10 saying? A particle moves in a surface of a sphere of radius r. The number of generalized coordinates required is 1, 2, 3, 0 cannot be determined. Okay. So the particle moves on a sphere. Particle moves on a surface of a sphere. Surface of a sphere of radius r. So for sphere, the generalized coordinates basically are theta phi, but the constraint is what is the constant here? The constant is that okay. The constant is particle moves on the surface of the sphere of radius r, right? So that means the equation of constraint for this is x square plus y square plus z square equals to r square, or let's say I will go r square equals to r square. So I can say that r theta phi r is constant. So generalized coordinate are theta phi. Okay. So we can see that the number of generalized coordinate is 2. This is theta and phi. So this is answer number 2. Okay. So for this, what we have done, we have taken the particle moves on the surface of a sphere of radius r. The number of generalized coordinates required is. So basically for sphere, we are having the coordinates as r theta phi. But there is another constant. The constant is r square. In the particle is moving on the surface. That means x square plus y square plus z square should be r square. That means r square should be r square. So the angle of theta phi r is constant. So the generalized coordinate will be theta and phi. Okay. Now coming to the question number 11. Which statement is true about the Lagrangian of a free particle? Okay. So A1, let me write here. that A is T minus D is kinetic energy and V is potential energy. Okay, so for a free particle, V equals to 0. Yes, so you can see that A equals to only T. So for a free particle, I'm talking if it is in Cartesian 2D. So it will be half m extra square plus y square. Or let's say I am talking about A equals to half m extra square plus y square plus z square. So that will be Cartesian in 3D. Now let's say I am talking half m r plus square plus r square theta dot square. So it is polar in 2D. And similarly, let's say I am having L equals to half m r dot square plus r square theta dot square plus r square sin square theta phi dot square. So it is spherical coordinate in 3D. So we can see for free particle L is exactly T as there is no view. Okay, now coming to the options. It must contain all generalized coordinates. Okay, so it must contain all generalized coordinates that may or may not be, may not true, because in 2D the generalized coordinate is 2. In 3D generalized coordinate is 3, and like that. So obviously it is not may or may not true. So it must not contain time explicitly. Yes, that should be true, because our kinetic energy does not depend on time. So obviously it must not contain any time explicitly. It always leads to correct equations of motion. That cannot or may or may not be the true one, because you can see that if I take the Cartesian coordinate in 2D, then the equation of motion will be different. If it will be a Cartesian coordinate in 3D, then the equation will be again different. So like that. So this is also may or may not true. It must avoid cyclic coordinates. It must avoid cyclic coordinates. That is also not correct, because we don't know. So we don't know that which type of T is there. So let's say if I am having T equals to half m x square plus y square. So here you can see that x and y are the cyclic coordinates, but z is not a cyclic coordinate. Okay, so for this case also it will not be the correct one. It must avoid all cyclic coordinates. That is not true. Okay. So for the Lagrangian of free particle, it must not contain time explicitly. That is the correct one. So for free particle L does not contain time explicitly. Okay. Now coming to the next question. The Lagrangian for a charged particle in an electromagnetic field is L equals to half m r dot square plus q r dot E minus q phi. The conjugate momentum is what? content of a charged particle of an electromagnetic field. Content for a charged particle. Electromagnetic field is L equals to half A matter square plus dot A minus Q phi dot. So for this case I can see that generalized coordinate is r only, because this is a function of r only. So the conjugate momentum is so conjugate momentum associated with generalized coordinate r is E of r, which is del L del r dot. Now our L is half m r dot square plus q r dot dot a minus q phi. So r dot pr is del L del r dot, so this will be half m r dot 2 plus q a, so it will be am r dot plus q a. So this is the PR, generalized momentum corresponding generalized coordinate r, which is PR m r dot plus q a. Now we have to see the option, which one is correct. Answer is m r dot plus q a. Actually it should be vector form, so you can see that option number 2 is correct. So for that question, what we have done, we have just written the a half m dot square plus q r dot dot a minus q phi. So the conjugate momentum associated to r is PR, which is del L del r dot, and it will be half m dot square plus q r dot a minus q phi. So we will just differentiate whole n with respect to r dot, and we got that m r dot plus q. Okay. For a particle with kinetic energy T, which is half r dot square plus r square theta dot square plus r square sin square theta phi dot square, the generalized momentum corresponding to phi is how much? Generalized momentum corresponding to phi. Okay, so what is here? T is half m r dot square plus r square theta dot square plus r square sin square theta phi dot square. So generalized momentum corresponding to phi. What will be d phi, which is del t del phi dot, or it will be del L del phi dot. Okay. So now we can see that del del phi dot of half m dot square plus r square theta dot square plus r square sin square theta phi dot square. So this will be nothing but you can see that. So phi dot square is only present here in this term. So it will be half m r square sin square theta 2 into phi dot. So m r square sin square theta phi dot. So finally we will have d phi, which is conjugate momentum corresponding to the generalized coordinate phi is p phi, which is m r square sin square theta phi dot. Now coming to the option. Okay, this is the correct option, m r square sin square theta phi dot. Okay, so for this case what we have taken was just taken to the particle with kinetic energy E is equal to half r dot square plus r square sin square theta phi dot square. The generalized momentum corresponding to phi is m r square sin square theta phi dot. So for that we have the T as this half m r square plus r square plus r square sin square theta phi dot square, and p phi will be del t del phi dot, which is del del phi dot again. So there is a v here for this case. So L will be exactly same as T. So del del phi dot of half m r square plus r square phi dot square theta square plus r square sin square theta phi dot square. So the answer will be m r square sin square theta phi dot. So p phi is m r square sin square theta phi dot, which is option number 3. Okay. Now we can go for the next question. Yeah. Question number 14. The number of holonomic constraints for a rigid body moving freely in 3D space is. Okay. So here we need to do something new. Actually, we need to know some basic differences between three terms. One is unconstrained coordinate, equation of constraints, holonomic constraints, then we need to know that it's generalized coordinates, and similar to degrees of freedom. So what are these? So first I just want to mention that generalized coordinates are exactly similar to as degrees of freedom, means the number of independent parameters we need for describing the motion of a particular system. Okay, fine. This is a generalized question. So that means this is nothing but the same footing as the degrees of freedom. Now coming to the unconstrained coordinates. So this is nothing but all possible coordinates to define the motion of a particle. So it will be like Holonomic constant plus degrees of freedom. So now coming to the holonomic constant. So this is exactly similar that the number of constraints means like you can understand that the oppositeness or to like the forces which can apply to oppose the actual motion of the particle. So this is the constraint. So the number of constraint applied to the particle. Okay. So now we can understand that unconstrained coordinates is equals to holonomic constant plus degrees of freedom. So similarly I can write here holonomic constraint is equals to unconstrained coordinates minus degrees of freedom, right? Okay, now coming to the question, the number of holonomic constants for a rigid body moving freely in 3D space. Okay, so they are asking about this, the number of holonomic constants. So for that what we need to know that number of unconstrained coordinates and number of degrees of freedom. Okay, and the particle is what? It is a rigid body in 3D space. So for this case, number of unconstrained coordinates are nothing but 3 into n. So it is, as it is a 3D space, so 3 into 3, which is 9. Okay, fine. Now coming to number of degrees of freedom. Number of degrees of freedom, which is 3 plus 3, which is 6. Why it is 6? Because maybe I can write here, yes, 6 degrees of freedom for a rigid body. How? It is coming as 3 translation, like shift the whole body along x, y, z. Okay, so it can be, so if I talk about like that in 3D space, one rigid body can space go here, and x, y, z both are all are free. Now 3 rotational. So how rotational? It is basically rotate about 3 axes. So now we can see that for a rigid body in 3D space, degrees of freedom is always 3 plus 3, which is 6. Now, the number of holonomic constants equals to number of unconstant coordinates minus degrees of freedom. So the unconstant coefficient was 3 into 3 minus 3 plus 3. So it is 9 minus 6, which is 3. So number of holonomic constants for rigid body in 3D space is 3. So maybe we can just from here, yes, so it will be 3. Okay, now coming, so what we did here for answering the question, so they are asking that the number of holonomic constants for a rigid body in 3D space is how much. So to know the holonomic constants number, we need to know the number of unconstant coordinates as well as the number of degrees of freedom. Because the unconstant coordinates equation of holonomic constants and equation coordinates, these 3 we need to know, and there is first of all generation coordinates is exactly similar as the degrees of freedom, the number of independent parameters we need for describing the motion of a particle. Moving to the unconstant coordinates, all possible coordinates to define the motion of a particle. So unconstant coordinates means the holonomic constant plus degrees of freedom. And what is holonomic constant? The number of constants applied to the particle. So unconstant coordinates was holonomic constant plus degrees of freedom. So we can see that number of holonomic constants equals to number of unconstant coordinates minus number of degrees of freedom. So the rigid body in 3 space, for this case the number of unconstant coordinates is 3. So n is the n dimension. So here it is 3D, that means 3 dimension. So the total number of unconstant coordinates is 3 into 3, which is 9. The number of degrees of freedom is 3 plus 3, which is 6. So how it is coming as 3 plus 3 equals to 6? 6 degrees of freedom for a rigid body can be told as 3 translational and 3 rotational. So 3 translational means it shifts the whole body along XYZ or at the y, whatever you want to say, and the rotational means rotate along the 3 axis for a rigid body in 3D space. Degrees of freedom, you can see that 3 plus 3 equals to 6. So the number of holonomic constant is 3 into 3 minus 3 plus 3, which is 3. So the number of holonomic constants for rigid body in 3D space is 3. This is the option. Okay, now we can come to the next question. For the kinetic energy, T equals to half outer square plus r square third square plus s square sin square factor square. The conjugate momentum for theta in the Lagrangian equals to T minus V r. Double is the momentum for theta. So here it will be minus theta phi. Because T was half here, momentum corresponding to theta. So what it will be? Half m r dot square r square theta dot square r square sin square theta phi dot square just a minute. Minus v r theta phi. So now we can see that so basically that theta dot. So theta dot means you can see that this one is only the function which is a r square theta dot square, and all other are totally independent of theta dot. So as this is a delta theta dot, so that means we can write half m r square 2 theta dot. So it is m r square theta dot. So this is p theta. So I can say that conjugate momentum corresponding to generalized coordinate theta is p theta, which is m r square theta dot. Okay, so this is this one. So for this case, what we have taken, the further technology plus r square theta square plus r square sin square theta phi dot square, the conjugate momentum for theta in the Lagrangian E equals to d minus v r theta phi is. So to calculate that one we have taken, we just write the Lagrangian, which is half m Laplace square plus r square theta square plus r square sin square theta phi dot square minus v r theta phi. So t is this one and n equals to d minus v. The conjugate momentum corresponding to theta will be p theta, which is del and del phi dot, and that means del theta dot. So that means del theta dot of all m, del theta dot of all these things. And now here you can see that in theta dot means there is only one term which is the function of theta dot, which is r square theta dot square. So simply it will be half m r square to theta dot r square theta dot, which is p theta. So the conjugate momentum corresponding to generalized coordinate theta is p theta, which is r square theta dot. Okay. Now coming to the question number 16. A particle moves in a potential. Okay. Which coordinate is cyclic in spherical polar coordinate? Okay. So a particle moves in a potential r equals to alpha by r, where alpha is beta than zero, whose coordinate is cyclic in spherical polar coordinate is theta phi. So first of all, in spherical polar coordinate, we need to write the n, which is t minus v. And v is given as alpha by r, where alpha is greater than 0. Okay, fine. So we need to see that t in spherical polar coordinate. So what it will be? In spherical polar coordinate, t is half m r dot square plus r square theta dot square plus r square sin square theta is a function of r dot theta dot phi dot r theta. Okay, now coming to L. Our L is t minus v, which is half m r dot square r square theta dot square r square sin square theta phi dot square minus alpha by r. So from this expression I can simply see L is a function of r dot theta dot phi dot r theta. Now we can see here the generalized coordinates are r theta phi. Among them r and theta are present in L. Also r dot theta dot are present in L, but phi is not present in L and phi dot is present in L. Okay, so the cyclic coordinate is phi, because cyclic coordinate means the coordinate which is not present in L but the conjugate momentum associated with that generalized coordinate is present in L. Actually, I should not write here conjugate momentum. It can be written as like time derivative of generalized coordinate. So yeah. But the time derivative of generalized coordinate is present in L. So now we can see that the phi is the only one which is the cyclic coordinate. So which coordinate is cyclic and spherical polar coordinates? So it will be phi. Okay, so here the phi is the cyclic coordinate, right? So now coming to the next question. A particle in 1D has a potential energy V is equal to half m omega square h square plus mu raised to the power 4, where m omega mu are constants. What is the conjugate momentum? Okay, the particle in 1D has the potential energy. So the particle in 1D, so 1D means the generalized coordinate will be on this x, because we can see that the momentum the potential is only as a function of x. So So the particle in 1D has a potential energy this. So the potential energy is half m omega square x square plus mu x to the power 4. Now we can see that in 1D the kinetic energy of that particle is T equals to half m x dot square. Why it is x dot square? Because it is 1D. So only one generalized coordinate, right? So this will be simply in 1D the Lagrangian of the particle is T minus V this. So the answer will be for here half m x dot square minus v. So half m x dot square minus m by 2 omega square x square plus mu x to the power 4. Now we can see that what they are asking, what is the conjugate momentum. Okay. So the conjugate momentum corresponding to x, which is the generalized coordinate, is P of x, which is del L del x dot. Now half m x dot square minus m omega square x square by 2 plus m by 2 omega square x square plus mu x to the power 4. So px is, okay, so this whole of x dot, so it will be del del x dot of half m x dot square minus m by 2 omega square x square plus mu x to the power 4. So from there I can see px is simply half m 2 x dot. So it is m x dot, because you can see that for v there is no function of x dot. Okay, so px will be m x dot simply. So this is the answer. So for this case what we have taken, we just write here the potential energy half m plus potential by 4, and the kinetic energy was half m x dot square, because it is a 1D. The particle will be in 1D as half m x dot square. So half m x dot square minus v. So half m x dot square minus m by 2 omega square x square plus mu x to the power 4. So the conjugate momentum corresponding to x, which is generalized coordinate, is del del x dot of L. I mean like del del x dot of L. So it will be m x dot simply. Okay. Now coming to the next question. Question number 18. A free particle moves inside a cylindrical tube of radius r. The number of generalized coordinates is. Free particle. First of all, we need to see the language, which is free particle moves inside a cylindrical tube of radius r. So free particle moves inside the cylindrical tube of radius r. That means if I want to draw the picture, so this is, let's say, r, right? So this is the cylindrical tube. So let's say I am talking about one particle which is moving inside of that. So it can move here, anywhere, as this is a free particle. So free particle means degrees of freedom will be simply 3. Okay? And inside the cylindrical tube, so if they are talking that inside of that cylindrical tube, inside, so generalized coordinates, which is degrees of freedom, is 3. Now I have one extra information. So let's say I'm talking that the particle constrained to move on the surface of the cylindrical tube. So for that, the number of holonomic constant is 1. So degrees of freedom is 3 minus 1, which is 2. So for that case, the number of generalized coordinate is 2, but the particle moving inside the cylindrical tube has generalized coordinate as 3, which is exactly unconstrained coordinates, because there is no equation of constraint. So the answer for this question will be 3. Okay, now we can go for the next question. The number of cyclic coordinates in the Lagrangian L equals to t minus v, where v equals to this. L is t minus v, and v of x, y, z is k x square minus y square minus z square. So for this case, we can see our A will be t minus k of x square minus y square minus z square. And for this case, the generalized coordinates are x, y and z, right? So the kinetic energy will be half m x dot square plus y dot square plus z dot square. Okay, so the Lagrangian will be t minus v, which is half m x dot square plus y dot square plus z dot square minus k x square minus y square minus z square. Now cyclic coordinate. So the coordinates, generalized coordinates, which are not explicitly present in L, but they are time derivative are present in L. These coordinates are cyclic coordinates. So for this case, where our L is half m x dot square y dot square z dot square minus k x square y square z square, the generalized coordinates are x, y, z, but all the generalized coordinates are present in L, and also x dot, y dot, z dot are present in L. So among x, y, z, none or no one is cyclic. So if L equals to half m x dot square plus y dot square plus z dot square minus k x square minus y square minus z square, the number of cyclic coordinates is 0. So you can see that the option is C. So the number of cyclic coordinates in the Lagrangian L equals to t minus b, where p x y z is k x square minus y square minus z square, with k equals to 0 is z. If k equals to 0, then all the x, y, z are canonical. Let me write here also. Our L was this. If k equals to 0, our L will be simply this. That means for this case, x, y, z all cyclic. Okay. Now coming to the last question. The Hamiltonian is defined as h equals to t minus v, t plus v, summation pi q by dot minus L, summation pi q by minus L, half m q dot square. So in Sar's lecture, we have seen that L minus summation pi ui dot was minus h. So h can be summation pi ey dot minus h and same. So that will be the expression for h. Now coming to another expression. This is a very general form. Now for mechanical system, our h will be t plus v, because we have seen that our a was t minus v, and for the mechanical system we are getting that a is equals to t plus v. So the correct answer for this question will be a is equals to summation pi ey dot minus l and a is equals to t plus v. Okay, so the answer will be this as well as this. So this is for mechanical system. Okay. So now maybe we can wrap up the session. So I am just going through the questions here, all the 20 questions. So this is the last question. For the first question. This is the first question. Now coming to the second question. Then third question. Fourth question. Fifth. Sixth. Seventh. Eighth. Ninth. Tenth. That was the system. 11. 12. 13. 14. 15. 16. 17. 18. 19. 20. So these are all the 20 questions which are very similar to the previous year week number 9. So Yeah, maybe we can meet in the next class. Tata.